Hello, dear audience. Thank you so much for being with me with another tutorial videos of deep learning. Okay, we introduce a cost function and said that it is commonly used and can tell us which W is good and which W is not good. And we talked about these concepts. Now, another useful function in this field is the softmax function, which is also called the multi-class logistic regression function. It has different names. This is also common, even more than the previous one. It is used in the discussion of artificial neural networks and deep learning. We are supposed to get the good or badness, goodness actually or badness of the wi that gave us these points from the points of the classes. Remember that these scores are a function of w and x. For now, we say w multiplied in x. Very simply, which will become more complicated later. One interpretation is that we consider these scores as logarithms of unnormalized probabilities. What does it mean? Not normalized means that the probability sum is not 1. For example, here this 3.2 is the logarithm of the probability of the cat class, but it is not normalized. Now, if we want to get the probability from these, that means we want to convert these scores into probability. The higher this score is, the more likely that class is to that input. We want to define a function that the higher the score, the higher the probability. It means that there is a direct relationship. The first thing we do is the inverse of the logarithm, that this logarithmic function is neutral. The opposite of logarithm is exponentiation. The first thing we do is to multiply e's to the power of the score of each class. Then, for the time being, we perform empowerment on the scores and the actually exponentiation, exponentiation on the scores, and they become normalized probabilities. Now we have to normalize. We divide these probabilities one by one by their sum so that they become normal. Well, it is natural that the class with a bad score is less likely. Now we get three numbers that add up to 1. These are normal. Now what we have to do is to find that W. If the input belongs to a class, the probability of that class will increase. That is, for example, here this 13% should be 1 and the rest should be 0. Then this was the best W. Instead of maximizing these possibilities ourselves, we can maximize their logarithm. There is no difference, and this is done for simplification to reduce the computational load. Well, we wanted to define the cost function and pay for something. It means that the more it is, the worse it is, and the lower the cost, the better it is. So we add a negative to it, and this becomes our loss data. Actually, now it does not always happen that the probability of the input data belonging to the correct class is 1. But we try to maximize this probability because the sum of these probabilities is 1, and by maximizing this probability, the rest of the probabilities will automatically become minimum. Therefore, we all try to maximize this possibility. We call this function softmax function. This loss is only for this function. We also calculate for the rest of the functions and get an overall average. Now we have x and we have w and b, and we want to know how good these w and b are for a particular data. We multiply w by x and add it to b. We said one method is a hinge function or multiclass SVM, and another method is the same method that we have seen now, called the max construction function. You can see that there's an indirect relationship in both. The choice between these two depends on the expert. And this is also a hyperparameter, but mostly softmax is used. In the example, I will explain to you why we came here and classified this data. These are points and have not yet become normalized and become a possibility. It does not matter for multi-class SVM cost function. It just says that you should choose the highest score. In the second row, the first score of one is more than the second and the third. It means that both in the first row and in the second row, the loss based on multi-class SVM is 0. It means that as much as the first one is good, the second one is also good, and the third one is also good. It means that they do not see any difference. And now, why have these points changed? Because the data has changed and this x vector has changed. And now, why has the data changed? Because of noise. That is, we want to say that this method is not very sensitive to noise, but softmax makes a distinction between these three chooses the third one, because the probability is almost 1. And it is the most desirable. You can definitely implement this in TensorFlow to understand more. Here we have 3 classes. That means we have 3 borders. So we have 3 lines. Classes are 2-dimensional. So we have 2 features. Here we also attached B to the W matrix itself, and it became 3 features. Blues belong to class 0, greens to class 1, and reds to class 2. Here you can set the optimal W by changing this manually. I suggest that you enter this link and try it yourself to get a better understanding. We introduced the cost function and said that we should minimize it. For this, we must use mathematical optimization methods. These discussions have existed in mathematics for years, but every mathematical method is not useful for us. Now this is a complicated discussion. But here I want to tell you a practical foundation that you can actually use. These sentences related to cost functions are actually a function of W that we want to minimize. One day is to find a good W by chance. If the number of parameters is small, this method may be useful, but it is not possible in the real world. Here we used a random MN function which works with normal distribution, and its probabilities are not equal. Most of the numbers that are the output of this code are from minus 3000 to positive 3000. This is luck. After thousands of test repetitions on the CFAR10 set, it has an accuracy of 51%, 15% actually. If we did it completely by chance, the accuracy would be 10%. 1000 repetitions, only 5% improvement. This is not a good number at all. This collection was made available to humans, and humans were able to recognize the correct class for each image with a 94% accuracy, because the photos are small and mostly of poor quality. Here with the random search algorithm, finally the accuracy is 15%, still far from 94% human accuracy. In deep learning, the goal is to reach the human in the first stage and surpass the human in the second stage. That is, we need at least a 95% accuracy in this matter. So this method is not suitable. There is a much simpler way. This is the shape of a landscape. Now we want to find a view in this mountain that has the lowest height, and we have an altimeter, actually height meter, I don't know, in hand. Our vision is limited, and we can see one step here and there. We'll look to see if take one step in each direction, 360 degrees actually, in which direction we have the greatest height reduction. We take the same step. We keep repeating the same thing until we finally reach the valley. Now this optimal point may be global or local. This idea is a very important algorithm called gradient descent. Now all applications and deep learning operators without the exception are performed with the same gradient descent algorithm and its family. It is very rare to use this expression without exception, but in this case I definitely say without exception. If you know the basis of this algorithm, you will understand the logic behind deep learning. This algorithm can be used in two ways. At any point we can estimate the gradient. We have the formula of the cost function, and we can get a differential from it analytically. The analysis is very simple. At each point we add a very small value h and calculate the value of the function and divide the difference between this value and the value of the function for the same point by h. The smaller this h is, it goes towards the differential. When we define this as slope, we want to have the biggest slope because the higher the slope, the fastest we move to the minimum point. It means we are getting closer to this point with each step. We give an example here. Suppose this is a vector w. Our whole goal in this lesson is to calculate the differential of this w. We said that the loss function is a function of w. Here our variable is a vector, which is not important at all. It is a point in n-dimensional space. The first thing we do is calculate the value of the loss function in this field. The more it is, the w's are bad. The worse actually the w's are. Anything less means these W's are good. Well, this becomes FW. We are going to move one particle, for example, the same H size in each dimension. I have nothing to do with the rest of the components. It gives me a new point. I will repeat this work. I calculate the function again at this new point. The difference between these two is divided by h, the slope in each component dimension. I mean, we repeat this every time for every dimension. Finally, this dw that is obtained is a vector that tells us that if you move in this dimension, you will decrease by this amount. That direction of movement is called gradient. This dw we have written is actually the same as dl divided to dw, which we have said and written here dw for simplicity, because w is a vector. That differential can also be a vector actually. This is the code that will do this for you in Python. This is called the numerical estimation method. This is one of the methods you can use. But this method is very slow. For example, if you have 100 elements and the training set has 50 million elements, it will take a lot of time, but this method is also approximate. The second method is the analytical method. We get differentials with the same methods of Newton and Laplace, and mentioned in which are mentioned in mathematics. We calculate the differentials of a function L with respect to W. The number of parameters is several hundred million. The number of parameters can be larger, and this is a problem, and it is impossible to calculate them manually, but we do not do this. The backpropagation algorithm calculates this dl divided by dw2, dl divided to dw1, and so on. You should first master these formulas and then use them in TensorFlows. This method is accurate. This is a gradient descent algorithm. It has a very simple idea. We calculate the gradients. Of course, we usually consider the step size as well. This step size is also called a learning rate. Note that the gradient algorithm calculates the maximum, and since we want to decrease in the opposite direction, we multiply it by a negative. This movement step is the most important and a troublesome hyperparameter. All implementations may take a week, but finding the best alpha may take several months. Alpha is the same step size actually. In the local optimum, the gradient is 0 and the algorithm converges. In practice, we arrive at this 0 answer. Usually, when the size of our movement becomes too small, we stop the algorithm. This contour slope, this contour shape is the algorithm. We use the color for the third dimension, dark color is low loss, and red color is high loss. In convex functions, we definitely reach the solution with any step size, but if the step size is small, the process will be long. If it is too big, overshoot will happen. This algorithm is not efficient because in every step you have to use all the data of the training set. Therefore, each step takes a long time and the cost of these calculations increases. Because of this, they usually close the training series and divided it into batches. They use few, maybe not many exact directions, but it is much faster. This number of training data in each batch is not a hyperparameter and depends on the GPU. 32 or 128 and 256 are common numbers that are considered for this purpose. Now, based on these 256, we determine the direction. That is, it's approximate and estimated. In fact, because of this, it is also called stochastic gradient descent. It also has a special mode that considers the data one by one, and this is not very common in the real world. Usually 80, 90 and 100 are used. You can see this decrease and the increase in the figure because it is an estimate, but the general trend is to decrease. You should draw this figure in all problems, whether in artificial neural networks or deep learnings. Suppose the optimal alpha gives us such a shape. If we consider alpha to be small, the slope of this decrease becomes smaller. Finally, we may reach the final optimal point, but with many iterations. The concept of epoch is that we said that in each iteration, instead of using all the data, we use a part of them. For example, out of 50,000 data, we use only 100 of them. So the size of batch is 100. We have 500 batches. If we repeat 500 times, this becomes an epoch. Epoch means to see all training data once. Each epoch takes time. So more epoch means to reach the result later. This time is very important. If alpha is too small, the epochs will be too many and the time will be too long. If alpha is large, we have a significant decrease very soon, but it gets stuck at this point. That is, we reached a local optimal point, and if it is too big, we don't have a decrease at all, and the gradient increases. So adjusting this alpha is very important. So the more efficient version is to use a batch form. If it is a question of maximizing, we should move in the positive direction. This is the most important artificial intelligence, machine learning, deep learning algorithm. Generalized methods are one of these algorithms. Here we see the shape of the contour of a function. Actually, the figure of the contour of a function. This red is the stochastic gradient gradient descent. Look how slow it is, but that one moves faster. The route is different, but the speed is higher. Different methods take different paths. What's suggested is the other method. These are available as packages and they're already in TensorFlow. In many opinions, it is better to use stochastic gradient descent first and then Adam and other methods. Okay, let's talk about back propagation algorithms. It doesn't matter how many parameters we have parameters w we have in the loss function. These gradients are used automatically. A mistake that happens even in university classes is that they refer to this algorithm as a method to optimize the neural networks, but it is not true. This algorithm only calculates gradients. For example, it provides stochastic gradient descent. So the algorithm is not optimization or training. Finally, we can change the weights in the direction of the gradient. What is our criterion for being good? The standard is minimization. We try to reach a minimum and be better than human. Actually, here the criteria of being good is human. The standard is human, and we want to minimize the cost to become similar to a human. So the standard is a human, and we try to reach a human and be better than human. We said that in practice we always use the analytical method, but in order to make sure that we worked correctly or not, we calculate both analytical and approximate methods every few steps, and if the difference is small, we make sure that we implemented it correctly during development. This is called gradient analysis. If you want to learn deep learning, you need to learn computational graph. All calculations in deep learning are layered. To understand this material here, to learn backpropagation algorithm. Until now, we had loss function. We would multiply the input vector and the weight, and it would be the score of the classes. After these classes, we calculated the cost functions. Showing these steps in a graph is called computational graph. The vertices specify the operation. Classifiers here are simple and do not have one more layer. In deep learning, it is more complicated and there are more layers. We start with a very simple computational graph. It has no more than 2 vertices. The backpropagation algorithm has 2 steps. A forward step where you start from the data and move towards the loss function. We call this step forward, and now we want to calculate the differential of this loss function with respect to each of these parameters. We have to go back to this graph and calculate the differentials. This stage is called backward or backpropagation. First, a simple example. We want to calculate the loss differential with respect to x, y, and z. So the goal is to calculate these 3 keys. If a vertex, its input is connected to another vertex, the value of that vertex must be calculated first. This is called topological. In backward, we start with number 1. because the differential of each parameter with respect to itself becomes 1. Now I spread this one, which is the gradient of f with respect to itself, backwards. We must return to the reverse of the topological order. We call d2 divided by, or in respect to the dy and the d2 and the dx local gradients because they only depend on this vertex and they have nothing to do with the rest of the graph. These computational graphs have been implemented in TensorFlow. All these and the implemented backpropagation are available, only you have to understand the logic. There is a longer example. This is the loss function of softmax. Well, the goal is we usually do not calculate the differential relative to the input. Here x is the input. The differential must be calculated with respect to the parameters that is relative to w0, w1, w2. We start from the end and come back. We have done forward calculations and found that it was simple. We start from the end. The differential of the loss function is equal to itself. The differential of each function is equal to itself. Don't care about all the graphs at any moment. Consider only the vertex you are in. We have the differential with respect to the output. We want the differential with respect to the inputs. All we have to do is multiply the differential with respect to the output by the local gradient. What is local gradient? This function is 1 divided to x. X here is a small 1. The differential of the division of 1 into x becomes the minus form of 1 divided to the second power of the same x. I multiply this by the local differential. It becomes the gradient relative to the output of this node. Now I have the gradient with respect to the output of this node. Here this minus 1 divided to x2 is the local gradient. This is the gradient I got so far. I will multiply these two together and it will be the gradient compared to this. Now I have the gradient with respect to the output again. I calculate the gradient with respect to the input. How? We multiply by the local gradient. This is a very simple addition function. The differential of a function that includes x plus a fixed number becomes 1. So this gradient is multiplied by a number of 1. So this is multiplied by 1. I will continue this until I reach the w parameters. This is what backpropagation does. Let's go back step by step in the same way. I recommend that you do this example by yourself. In this way you will understand the material better and the concept better and come to a series of points. For example, you will understand that when we reach the sum node, we should spread the gradient very simply, because for example when z is equal to p plus q, the differential with respect to q is 1, the differential with respect to p is also 1, so the gradient is distributed unchanged So in the sum node, the gradient transferred. In a multiplication, the gradient is switched, and in max node, the rotation will perform actually. For example, in multiplication, now we have the whole differential of this function with respect to W0, W1, W2. We wanted the same, and now that we add the current W with the W's, it becomes a new point. Sometimes, for example, in TensorFlow and similar environments, this whole thing is called softmax or sigmoid function, and they implement it as a node. That is, in this way, our graph will shrink. These are node clouds. We combine a set of operations in one node. Well, as I said before, there are a series of patterns. For example, when you reach the sum node, the gradient that exists here is distributed in the existing path, or at the multiplication node, the gradient is switched. This two multiplied by 3 becomes the lower gradient. And multiplied by -4 here becomes the upper gradient. It means that they switch together. Or for example, routing is done in max node. It sends to the one that is more. That is the gradient goes towards the larger input, and the gradient corresponding to the smaller input becomes 0. What if they are equal? It goes towards one of them, and it doesn't make any difference. There are the same points where I say that it does not have a differential function, but it has subgradients. We call them subgradients. If both were equal, we send the entire gradient to one and 0 to the other. When we have a node and we calculate how much effect the output of this node had on the final output of this graph, this node has an influence through the path of upper nodes in the output graph, and an influence through the path of lower nodes. If we add these two effects together, it becomes a total effect. So knowing these patterns is necessary in implementing deep learning algorithms. When you work with TensorFlow, you will see that this is the case, but a designer has already considered this for them. We have a forward and backward action. All operations are defined in this way. You just have to make this calculation graph, and it will do the rest of the calculations for you. Special example. Multiplication gate. In forward, we calculate the loss function, and in backward, TensorFlow calculates the differential and adds them together, and it becomes the final round. This is the basis of TensorFlow. Note, this is similar to a Lego game. In deep learning, the goal is to put these bricks together in such a way that we get a larger network that can do what we want. In these discussions that we had so far, the inputs were numbers. It was a scalar. It doesn't matter now. In neural networks, these are vectors, but it makes no difference. The calculations will be different, but the logic is similar. If you want to implement the backpropagation algorithm yourself, first you must implement the forward step. You have to calculate the score from X and W. Based on the score, we calculated these margins, we calculated this data loss from the margin, we can also calculate the cost of regularization from W's, and now we add these two together. This is the loss function and the forward step. Now we want to go back and calculate the differential of this function one by one. Here we have to follow the reverse topological order. In forward, first we calculate the score and then we calculate the margin, and then it's time to calculate the differential with respect to the score. If this pattern is formed in your mind, you can solve any complex algorithm. If you really want to understand the topic, you must implement this algorithm manually at least one time. We come to neural networks. Now you know what is needed in theory. What is a neural network? So far we have defined the function score. We said that X is the input and W is the weight. The linear score function, which we call the linear classification, was the multiplication of this W and X was equal to F. Now what is a neural network? We will calculate this W multiplying X, then we will apply a nonlinear function on it. Now I will explain the reason, and this part is very important. A simple nonlinear function such as max function, the maximizer function actually. If you calculate W multiplying X, a series of numbers will be obtained. We used to consider these numbers as the final scores, and now we consider them as intermediate scores. These are not final. It means that there is still work to be done. The first thing I have to do is to consider the negatives as a 0. Between Wx and 0. The maximum is Wx actually. And now we consider this maximum as X, that is a new set of features. Here the raw pixels themselves were input. I came here, did some work on X and created some new features. This will be a new function score. We call this a two-layer neural network. The upper part of the neural network was a single layer. Previously we used to perform calculations directly from the inputs. If you consider CIFAR10, the data volume was 3072. If we add the bias, it will be 3073. We had 10 classes. We wanted to categorize these 3073 pixels in 10 classes. In direct linear classification, we used to do this. Now a layer is added. First we multiply X by W1, which are a set of values is obtained. we must apply a nonlinear function here. It becomes a new value. It means that there was a vector. This is a new vector. We already had a bunch of features, and now we have a series of new features that were calculated based on those features. So the only thing this layer did for us was that it processed these primary features and gave us a series of new features, and now we do the classification based on these features. That is, this piece is exactly the same as the top. Instead of x, we only have h here. Now we multiply h by w2 to get the scores. Now if our network has more layers, we can calculate more complex functions. Remember we said that the linear function can only classify simple shapes. As we increase the number of layers, the shape of this function becomes more complicated. So you can do more complicated things. And the idea of deep learning is to increase the number of these layers as much as possible. But why couldn't we do it until now? I will explain this. Well, suppose we make it three layers. Repeat the three-layer neural network with the same steps. Again, we apply another nonlinear function on the output of the previous layer. Usually the max function is called the rel function. This was a new set of features, and now based on the result we will calculate the scores. What is the point of adding the number of layers, and what is the role of this nonlinear function? Suppose we did not have this nonlinear function. Suppose we take the nonlinear function. What would this function be? For example, f the multiplication of W3 and W2 and W1. The product of three matrices becomes a one matrix. Let's call it generally W. That is, this is also a line. So if this function is not nonlinear, increasing the number of layers as much as you want, you still have a function like linear classification, and you are only able to solve simple problems. Linear categories are useful for cases where data can be separated by a line. They have very little use in the real world. Theoretically, you can calculate any computable function with these multi-layer neural networks. We call this neural network two layers. But in terminology, some call this a hidden layer. One hidden layer. That is, some experts call it double layer because we have two steps of calculations and two W. The X's are called the input layer, the S's are the output layer, and the H's are called the hidden layer. But some people only count the hidden layer. But I myself consider this neural network to be two layers. And mathematically, it has been proven that any function, no matter how difficult it is to calculate, can be calculated with a two-layer neural network. We have been doing the same until now. There are always at most two hidden layers in neural networks. Couldn't you have 3 or 4 hidden layers? What is the deep network? The number of layers is more. You calculate H1 and H2. You calculate H3 from H2 and so on. That means you have a hierarchy of layers. Adding layers keeps making your function more complicated. Therefore, you can constantly solve more difficult problems. Why didn't we do this until 2012 or 2013? Well, there are different reasons. Deep learning algorithms were proposed in theory since 1984, but they were not practical until 2012. Okay, thank you so much for being with me in another tutorial video of deep learning. Please stay tuned to uh, get the delicate points in the upcoming lectures. Have a nice day.